Welcome everybody, my name is Eigenmann and I'm going over the in situ monitoring of curing reactions with mid-infrared dual-count spectroscopy with microsecond time resolution. So what's on the agenda today? We will talk about the technology, or I will give a brief overview about the benefits of dual-count spectroscopy, then some validations which I presented already in 2019. With some curing results at that time, the validation also with stepscan FTIR, quick comparison there. Then the body of the talk will be about the in situ monitoring of those curing reactions with mid-infrared lasers, where we can do this outstanding 1,000 spectra per second continuously. And then for even a small part of time, for 255 milliseconds, for microsecond time resolution is possible. Give a quick outlook what we've done with dental curing applications, where we also have the possibility to monitor single-digit kinetics. And as to wrap up the whole session, a quick conclusion and an outlook with channel applications where we currently work on, where speed is of importance. There are several benefits when talking about dual-count spectroscopy. One is the speed advantage, which will be, as I mentioned, the body of this talk, with high time resolutions in the order of micro or milliseconds. One is the brightness. The dual-count spectrometer is using a strong laser source, strong laser sources which are in the order of some much stronger, order of some magnitude stronger than thermal light sources. Another one is complex mixtures can be identified with due to that when we record several laser lines, so the multi wavelength recording. And last but not least, there's the high spectral resolution version of the IRsweep, which allows to record milli-wave number resolution. How does that work? How does dual-count spectroscopy work? There are two frequency count beams mixed on a beam splitter and detected on high bandwidth MCD detector. So each pair of those optical modes produces a radio frequency beat note, and the radio frequency spectrum can be measured with conventional electronics and represents the optical spectrum. Why is that fast compared to other spectroscopic techniques, for example, FTIR spectroscopy? So there are no moving parts. So those strong lasers are used to enhance the signal to noise. And actually, the signal to noise you can see here is in the order of, you can't see it here, but it's in the order of, as the noise is less than 10 milliodes in 1 microsecond integration time. And that allows to record single shot analysis and very fast microsecond time regime. So with an open measurement, an open beam measurement, just empty measurement is here in the spectrometer. We present here a heterodyne signal, which were obtained with a 1650 laser, which is often used in polymerization reactions, such as the curing results I will present. And I overlapped actually once a hydro and water vapor spectrum, which shows the information on the primary heterodyne signal in the same range. As mentioned before, we focus today on the speed advantage of dual-count spectroscopy, and there are some data of an early publication with Tillman Koltke from bacterial rhodopsin. And this bacterial rhodopsin cycle is repetitive. It's a protein reaction, and therefore actually also other technologies like stepscan FTIR is possible. On this slide, however, you have quite a lot of information. You see on the y-axis here that there's the spectral resolution in wave numbers. It's a very technical slide, but it's actually nice to understand a little bit the relationship of the spectral resolution and the time resolution. And talking about most of the FTIR spectrometer, which are currently available on the market when we use rapid scan, which is needed for such reactions, which are single shot reactions, they're all having actually the limit in the millisecond time regime. So looking at the x-axis, you see the range from 1 second to 1 microsecond. And you see there are some early FTIR homemade spectrometers built here with very high time resolution and also good spectral resolution, around 5-8 numbers. But the signal to noise was not good enough. And actually, we are very proud that Joachim Heberle was one of the first users. Actually, he is the first user of a dual-com spectrometer because he was just not satisfied with the signal to noise in this area. Again, it's just to give a little bit an overview about this new technology and how the IRsweep looks like. It's a benchtop spectrometer with easily exchangeable laser modules. You can see that here with Pierre, one of our senior engineers, is changing such a module. So the minimum requirement for such a customer-provided solution, also for example, if somebody is using their own chiller, is 0.05 Kelvin. You see here he disconnects the laser module and then he puts another one in here. In that case, it is the same, but that all can be done in 30 seconds. Of course, you need further 20 or 30 minutes stabilization, and then you're good to go for another measurement at another wavelength range. There are two main lasers I want to highlight because they were mostly used for curing results, the results which I will present in the next couple of minutes. There was one at 1650. It's an M1 laser. We call that also an M1 laser because most of the changes are done in that area, which is also very important for protein analysis, protein dynamics. And then another one, it's at 1300, where we did also quite a lot of measurements in the dental curing industry. Also an illustration, as you can see, I like pictures. There is a nice setup of this dual-com spectrometer where you can use actually all those currently available, commercially available accessories like stop flow accessories from TGK Scientific or Biologique, or there's actually ATR units. Probably one which is the most famous one is a Golden Gate ATR. And then there are also possibilities of using gas cells or transmission cells or connecting fiber optics and so on. I will not dive here into details. Going back to ATR, what does ATR mean? It's Attenuated Total Reflection. It's actually a very versatile tool for FTIR measurements, or specifically now also for dual-com spectroscopy. That's actually a technique where you can just apply the glue. That's in this case glue which is from kindly was provided from DELO. You put on top of it. You just need a small little part. You see here actually in the close-up that there was only a square, probably 2 millimeter used, very little material, and then you can do this in situ curing from top. An alternative accessory, which is done or constructed or developed by Irubis, is such a 3D printed device. So this is very cost efficient, a very cost efficient accessory where the silicon chip is optimized for laser spectroscopy. And such a chip is just also, that's also probably very interesting. It's only 50 francs and can be used typically for several measurements, specifically when you can clean the glue very well, which was the case with those measurements we did for the company DELO. So the material we were using the most for those measurements, which I will present, is PHOTOBOND 8484, which typically occurs in sorry, 3 to 5 seconds completely. So it's a very interesting material because so far most of the glues are probably taking a little bit more time. And So here on that slide, you can see in live the reaction monitoring of this glue. And it's nice actually with the offline measurements, it compares very nicely at 1655 and 1630. That's actually how you do that, or how it was done with a lot of FTIR spectrometers before and after curing. There's rapid reaction monitoring with 1000 spectra per second, gives a very good signal to noise ratio over, with a recording of 1 millisecond. And at that time, at the beginning, we did that with 440 spectra. And as you can see, there's also some really nice isosbestic points at 1666 and 1644, and another one at 1660. Isosbestic points, those are just points which are not changing spectroscopically during the measurements. Here again, if you just record the different spectra at early times, probably 2 or 3 years ago, we had this recording with 40 millisecond increments. You can nicely actually follow now those traces. One of the traces is actually a CC double bond, which you can see here in gray. And sorry, the CC double bond is the one, yeah, it's the one in gray, and in red, it's the carbonyl band, which is decreasing. That's the ketone of this acrylate. So those time-resolved measurements, specifically at the beginning, gave a lot of insights for new processes. And since the time resolution is that high, there's even an intermediate, which is possibly can be seen after a few milliseconds due to a slow lamp turn on, which might be smeared out at the beginning with other technologies. So we use this technology also to monitor another application, specifically when speed is needed. I mentioned that before, specifically for the dental curing industry, it is important to find new materials which cure faster, and chair time, that's the time a person sits at the dentist on the chair, obviously, should be minimal. And so for that, we used again the same Irubis chips and the dual-com spectrometer approach. And to do the irradiation, we used also a light. In this case, it was a blue light to start the measurements. So the goal was not to create some red teeth, obviously, but it's nice here just to illustrate. It was to monitor also in situ some very fast processes, which cannot be recorded with other spectroscopy technologies. Sometimes you can even see some strain releases events, for example, cracking. That's actually when the contact is not that good anymore with the crystal. So those results actually then in some vertical changes, which you can see here in the graph, in the time traces at around 4 or 6.5 seconds. Then what I mentioned before, it's some measurements at another wave number. So we changed actually the lasers, the laser module, and we measured here 1300 wave numbers, which is also a great use for this dual-com spectroscopy technique. So a very fast change, and we got some other nice information. And the great advantage is actually that you can even see that it's not only TK, it's also a small little shift specifically here. And having actually this great time resolution and spectral resolution, you get a lot of additional information. On the lower graph, and I zoom in here a little bit, you can see actually also the slow curing without light, so without light at all at the beginning. You see also already when there's probably a little bit light, sunlight can start the curing already. So it was not, the first measurements we did was not completely dark. And then it starts here, and you can see the other effect which needs to be controlled as well is like how thick the layer is. So because we control from the top, before we at the beginning we were also not controlling that. So the light, of course, the thickness, of course, has an influence in the curing as well. I mentioned as well at the beginning, and also to conclude, there are a lot of general applications which dual column spectroscopy offers, and every time when speed or high spectral resolution is of importance, there are a lot of applications which this can be used. First, actually, it's like protein dynamics. I showed a few examples where folding or unfolding proteins need to be observed. Specifically, some irreversible processes for the combustion industry, for the combustion diagnostics, where such reactions go typically 1 or 2 milliseconds, where you need also high time resolution, and then stop flow applications, microfluidics, spectral electrochemistry, you name it. I will not go through all of them, but there are quite a lot of high time resolution applications which might be interesting to check that a little bit clearer. A quick update about the general advantage for those industries, specifically here for the UV dental curing hardening, is that you get a big benefit of the single digit reactions, so that you can monitor those over a few seconds, and also to monitor the polymerization degree. Again, that's probably just a repetition that the technology has no movable parts at all. The quick highlight and the summary of the results we achieved actually over the lockdown. That was actually a big advantage for IRsweep, that we increased not only the continuous recording, where you can do 4 microsecond time resolution, you can do also for several seconds now the monitoring up to 1000 spectra per second since August this year. So this is a very outstanding possibility that you can not just monitor the beginning, because a lot of people are interested also in a continuous reaction monitoring in situ, as I mentioned before, for example, with the dental curing or curing in general. And since actually I cannot be live during the Q&A, I'm actually on a plane, but I'm very happy to answer your questions, or I can be also contacted by email or phone. I'm very happy actually to get back to you if you just shoot me an email on Eigenmann@irsweep.com, or just call me on or you will find actually also on the page. So thanks very much for your attention and enjoy the show.
So as you heard there from Florian, he's can't be with us for